разрешайте?
Да, все.
So thank you for the invitation to speak. And
По-английски это не invitation, это твои как служебные обязанности. Да, правильно насчет ПНД ты сказал, да? Что я не успел, хотел ВДР, СРД тоже хотел все расшифровать.
So I will speak about some class of singular symplectic varieties, meaning Poisson varieties. Finally, many symplectic leaves. So one of them is open.
One of them is what?
Open. This is
А это тождественно язык.
like for example, you can take A2 modular some finite subgroup, Lenin singularity. So
this is how you define it.
So you mean that symplectic form just in this in the
For the
first
school,
place?
yeah.
It's something. What is wrong with it? And so
with what?
with symplectic form, so you have symplectic form on A2, yeah?
It's not.
Yeah, but this thing is singular.
Yeah,
And
yeah.
you cannot say that it's symplectic.
Yeah, but you
the
can still say that
open
it's
small
Poisson.
part is symplectic, and it extends its Poisson structure with finally many symplectic leaves. Okay, so
And what's gamma here?
gamma is a finite subgroup in SL2.
Which is SL2? Just SL2?
SL, yeah, just SL2.
It was also made for A2 and right?
Pardon me?
Also made for A2 and S to right?
Yes, no, there are many examples, yes. But, so the title is Cherkis, Nakajima, Takayama, Bow varieties, and I want to start with a list of examples that are all contained in this class. So quiver varieties of type A or maybe A tilde, so it's a flat cyclic quiver. And this is just shall I recall what is a quiver variety? Okay.
What is Poisson structure of this?
Yeah. So it's sometimes denoted M0VW. And here, so here, V is V1, and then V2, some finite dimensional vector spaces, Vn. Or maybe they close up in a circle, and then these are gauge spaces, and there are some framings, W1, which may be 0 or empty. In fact, those two. So everything may be 0 or empty. Wn. And then this is defined as a certain Hamiltonian reduction. So you consider well, first of all, you choose some orientation, for example, like this. So you take a direct sum of from V I to V G. And also sorry, to be VI plus 1, because there are just arrows like this. And home from VI to WI. And then you take the cotangent space of this linear space. So this is just linear symplectic representation of the product of GL VI's. Okay, and certainly this product respects the natural symplectic structure here. So you take the Hamiltonian reduction. Meaning the spectrum of invariant functions on the zero level of moment mapping.
Well, is that a claim like imagine zero factor of the moment that is reduced.
What is the zero?
The zero, what is the moment map mean? The moment map is from, well, let's call it M. So it's via killing form, it's isomorphic to G, and it's just the direct sum of all GL VI's. And
this is clear. How different the moment was.
yeah, so we have those maps A1, A2, so A and minus 1, and then in the cotangent bundle we also have the maps in the opposite direction, B1, B2, B and minus 1. Also we have those maps. And the maps in the opposite direction. So these are called P and P1, and these are called Q1, Qn. Okay, so mu of all this хозяйство is the commutator of A and B plus PQ. Okay, and I can put indices here, but maybe it's even clearer without indices.
Well, it's like an AD.
Absolutely, yeah, it's just all, has the origin in ADHM, yes. So that's it, and as Roma says, the zero moment level is reduced, and so this is also some variety, and in fact, it is of this type, of the finitely many symplectic leaves. Also, you can take here the GIT reduction, so you impose some stability condition, and you will get some symplectic resolution. Semi-small symplectic resolution. Okay. So this is already a pretty wide class of interesting
So
varieties.
you never mentioned what's the ground field. Maybe
Complex
it's
numbers.
C.
Yes. So this is something. It can, well, well, it contains, for example, so already this subclass of Quiver varieties of affine type A contains, for example, Uhlenbeck compactification, although it's not really compact, of the moduli space over S, U, and instantons for also on the E space A2 modular Z and LZ. Or maybe you take it. There's a resolution of this Kleinian singularity, but only of this Kleinian singularity. I mean, you can also consider other Kleinian surfaces, but they will not be in this class of examples. So this class is wide, but not too wide. It does not contain instantons on A2 modular icosahedral group.
What is how they connected?
Anything. Well, it depends on your choice of V and W, but hell can be anything.
So
what
what
else?
is this simplest example, which is not well known but not in this class? You just said that
In instantons on Kleinian surface not of type A. Dihedral, for example, or tetrahedral. Okay. Then what else? It also contains, I mean, it's just the Quiver varieties also contain nilpotent orbits, well, maybe closures. O lambda in the nilpotent code of GLN. And Slodovitz slices. So probably I should also recall what is a Slodovitz slice. So you take an nilpotent element E in certain nilpotent orbit. So lambda is a partition, okay, because the nilpotent classes are classified by their Jordan types, partitions. And we take an element of this type, extend it to an SL2 triple, EHF, in SL10, and take E plus the centralizer in SLN over F. So it's an affine subspace, a vector subspace shifted to this E. So it's really a slice to this orbit. It's a theorem by Slodovin. This is called S lambda. S lambda is transversal. Slice O lambda, which generalizes constant slice to the regular orbit. And we
what's the dimension of S?
Lambda, the dimension of S lambda is n squared minus, or maybe if you in SLN, then S squared minus 1, minus the dimension of O lambda, which is given by some combinatorial quantity, which Roma only remembers. Yeah.
You say that S lambda is
Transversal.
symplectic or Poisson? What?
No, I only say the following, that given another partition, say mu, mu, that is bigger than lambda, so it dominates, which is equivalent to O mu closure containing O lambda. We can consider S lambda intersect O mu bar, and this will be singular symplectic.
But O mu is symplectic itself, right?
Yes, but you can now intersect with slices not to zero, but to some intermediate nilpotent orbits. Why not?
You just restrict symplectic form to
Yes.
something.
Okay. So these guys are examples of such equivalarities. For appropriate V and W, I will, in fact, say explicitly what are V and W in due time. Okay, so what else? What other examples will we have? Like we can consider the flag variety of again SLN, and now we can consider this certain Zastava space, namely the space of based maps of degree alpha from projected line into this flag variety with some particular choice of flag. Okay, and these are the same as moduli space of Euclidean monopoles, well, SU monopoles of topological charge alpha. Alpha is just n minus one tuple of positive images. So now this is an example of Boole variety.
Alpha is an element of what?
Alpha is an element of this positive code. Just degree, topological degree, the second homology of
That's what I was asking.
that. But it must be, so these maps, I mean holomorphic maps. And due to this holomorphicity requirement, the degree must be positive in this sense. So this is an example of Boole variety, but not equivalariety. Okay. We can also consider an affine version of this. So V is now the flag variety over S, L, and I. And then instead of Euclidean monopoles, from the point of view of mathematical physics, you get calorons. Okay, what else? Also, you can get monopoles with singularities. And colorons with singularities. Okay, so maybe that's enough for the advertisement for the list of examples. And just one last example. So all those pure varieties M, E, W are so-called Higgs branches of appropriate quiver gauge theories. And mathematically, it's just a tautology, it's just definition. When you say those words, you mean just this. Just that. Nothing else. But also, there are certain MC, W, these are so-called Coulomb branches. And they have some. Yes.
First case, is it M not or just M, the Higgs branches?
You have two versions. One is affine but singular, another is smooth but not affine, only quasi-projective.
I mean that in just that in definition which you said this is only here some holomorphic relations, yeah, which are called F terms in physics, but there are also D terms. I think that well, when you have these D term conditions, is the same like you impose this some stability conditions or things like that.
I just don't know. I never.
No, like if you
heard about D terms.
ADHM, yeah, you can write down this equation, which was written, or you can also write something which contains PP bar, QQ bar.
Oh no, the equation is the same. You only take some open part of this. The equation is always the same, just the holomorphic equation, nothing else.
Holomorphic.
Holomorphic, absolutely, yeah. And you just impose some open condition. In addition to this closed condition, you impose.
Often you can describe the result
Yes.
in other terms. In terms of so-called hypercarrier.
Yes, certainly. Yes.
Then you deal with real equations.
Okay.
Yes. This is what I mean.
Yeah.
Okay, maybe. Okay.
Of course.
But
And then I felt that you get not M not, but M, smooth on itself.
Then, well,
Sure.
But you are not
no,
interested, right, in such picture?
in such subtleties, I'm not interested at all at the moment. But when you take hypercolor reduction, you must specify your moment level. This moment level has complex part and real part. So here I take complex part always 0, but real part here is always also 0. But you can move it in the hypercolor picture to some positive chamber. And then you will get the smooth portion like this. So you will really change the moment, hypercolor moment level. Okay, so you also have some Coulomb branches that do have mathematical definition, but I will not give it. Okay, and then the relation between Higgs and Coulomb branches of the same theory is something called symplectic duality. But it's just in case it's not S duality, it's symplectic duality. And the maybe archetypical example of such duality is when you have like O mu bar as lambda, here. Then on this side you will have all lambda transposed intersecting with S mu transposed. Okay, they're symplectically two. So for example, if you take the whole minimal nil-point orbit intersect with the slice from zero, so nothing. The whole minimal nil-point orbit will be S dual to the slotted slice to sub-minimal nil-point orbit, which is declining singularity. So here A2 modulo 0 and 0 will be dual to subregular, yeah, sorry. I wanted to subregular slice. So a minimal of S n plus 1 is dual to this.
Does exist some definition of split duality as well? Or it is just
No, it's some phenomenology. So you have to, there is a construction of many examples of symplectic duality, and then there is a list of properties that the dual pairs satisfy. Maybe the most striking one is the so-called Hikita conjecture, which says that the, well, so if you pass from here to the resolution, like Springer resolution in this case, or Coué resolution like here, then the cohomology or ring of this resolution will be equal to the fixed point set of functions on the fixed point set of certain torus action. But as you mentioned, the resolutions are indexed by certain chambers, and the tora action are also indexed by the same chambers on this side. So there is a matching condition. Okay.
But these examples are inside this.
Yeah, inside this class, yes. So what I want to say is that those Coulomb branches also will always be in Cherkes, Nakajima, Takayama varieties.
I think you say more than the Coué varieties.
No, the Higgs branches are Coué varieties just by definition, but the symplectic duals, Coulomb branches, will be Bobo varieties, not Coué in general.
In general.
Yeah, in some particular cases, like this, you see that they are all Coué, but more generally.
Is it possible to have self-dual?
Oh yes, certainly. If some partition is, if lambda transposed is mu, then. Yeah. Okay. So. Okay. So now let me explain the construction of Boole varieties. So it is, it proceeds in the framework of Moore, Chikawa category. So the objects of this category are reductive complex groups. And in fact,
In GLL.
yeah, in our case, it suffices to have just GLL. We'll need nothing else at all. And morphisms. They are singular symplectic varieties. Equipped with the Hamiltonian action of G1 times G2.
So the circle is two comma one how you suppose
Isomorphic classes.
maybe no point.
Down to two categories.
Yeah.
Thank you. So composition. So from G1 to G2 to G3, there will be X and Y. Y composition X will be just direct product X times Y, and then you take Hamiltonian reduction with respect to the diagonal copy of G2. Okay, so for example, the identity morphism from G to G is the cotangent bundle of G. Okay. Now I will just list some basic morphisms, and both varieties are their compositions, and that's it. Over just two morphisms. So you see, our objects are numbered by positive integers. So I have either so for
two types
for types, yeah. So for V1 and V2, there are dimension of those V's. We can have either a morphism like this, and this is called NAM or triangle part. Or else we can have V1, V2, and this is called bifundamental or else two-way part. This.
Why?
So both of them are with the action of GL V1 times GL V2. So it acts here or there. So there's morphism from GLV1 to GLV2. So the bifundamental part is just what we had before. V1, V2 is the cotangent bundle to go from C V1 to C V2. What is more interesting is this NAM or triangle part, which is defined as follows. So if V1 equals V2, then the NAM part is the cotangent bundle over GL V1 times corresponding topological representation. Now, if V1 is bigger than V2, then this is GL V1 times certain slot of a slice. But the whole slot of a slice, not the intersection with certain nilpotent orbit, but the whole thing like this. I only have to say what is lambda. And lambda is V1 minus V2, and then many ones. Okay? It's a partition, just a hook type partition. Okay? And the topological recursion proves that in this case, it's not working. I mean, Maxim is sleeping and even not wakes up at the mention of topological recursion.
But topological recursion, you mean that topological recursion?
No, I don't need it. I just wanted to wake him up. So, this slice, whatever it is, is embedded as a finite space into GL V1 in this case. Okay? And this is the same as by killing form GL V1. And so this is embedded into the cotangent bundle of GL V1, which is V1 times GL V1 okay, so the point is that if you take the standard symplectic form on the cotangent bundle and restrict it to this so-called equivariant slice, it's still symplectic. So it's a symplectic subvariate.
But you probably mean the symplectic structure different from.
No. Just this one. Just you take this symplectic structure, restrict it to this. Why?
Because you eliminated coordinates in simple terms. You
Yeah.
eliminated part of coordinates which are purely isotropic. You eliminated just a part of momenta and left all the coordinates intact. So you have more coordinates than momenta is there.
I would even ask more simple. I don't see why it is even dimension.
Just because all the nilpotent orbits are even dimensional. Just because all the nilpotent orbits are even dimensional.
But you have GL1, GLV1.
Yes, and this is the slice in GLV1.
Yeah, but GLV1 itself.
It could be no.
I guess there's something more intricate is here. You have several several ways to identify the cotangent with the direct product. And probably you, for symplectic structure use one, and for embedding another one. Something like this.
With respect to left and right action, you mean?
Yeah.
Okay.
It couldn't be that straightforward.
Okay, yeah, and in fact, also from those two identifications, you see that you see that well, this nilpotent element, the hook nilpotent element, it's stabilizer in GL V1. it certainly contains GLV2. Just because it has V2 many ones. And so you have the action of GLV2 on this slice. Okay, and on the whole, you have the action of GLV1 on the left and of GLV2 here and just by conjugation there. On the right here and by conjugation here. So I want to say that this triangle part is good with the action of GLV1 times GLV2. That was absolutely evident for the bifundamental part, but also it works for the norm part. And now let me explain why is it called triangle part.
And this is symmetric, yes?
Pardon me?
When the V2 is bigger than V1.
Yeah, it's symplectic.
Yeah, it's symmetric.
Right. Yeah, so if V2 is bigger than V1, then you will get G V2 times slice V2 minus V1, 1. No. You have arbitrary morphics, arbitrary symplectic varieties with Hamiltonian action, but we'll need only those two. From those two, by their compositions, we will obtain arbitrary Bow varieties. So an arbitrary Bow variety will look like this. V1, V2, V3, V4, V5, and like this. So it will be just compositions. No, not necessarily. You can, well, you can have 0 here, and then V1, V2, V3. So then you can erase the 0 part.
Yeah.
You want to play something non-defined.
They can be empty.
But yeah.
Is FGRN you accept this reductive group to be other text?
Pardon me?
Is FGRN, I mean, your definition?
No, I only, the general Monte-Chikava category is pretty rich, but
Yes.
I only restrict myself to very special cases.
Yes,
The groups are only GLN,
Yes,
and models are only of those two types.
and for other types, can you also define the Bow variety?
For example, if you take classical groups like orthogonal and symplectic, you will get so-called orthosymplectic Bow varieties. But this is not yet written down by Nakajima, so I'm not talking about it. So more about now equals triangle part. Because giving a mathematical talk, I do need to write some formulas. And I will write some formulas here, but no more formulas. Just so V1 triangle V2 is called triangle because it is also isomorphic to the following thing. The maps from C to V1 to C to V2 then also have an endomorphism B1 here, endomorphism B2 there. We also have a linear functional here and a vector there. Such that something similar to the ADHM equation is satisfied linear space of such vectors, covectors, and the modules is not symplectic. So this is not really a moment map equation. It's only some mock moment map equation. But still, also you need to impose two open conditions.
So this is independent of whether V1 is equal to V2 or not.
Absolutely, yeah, uniform definition. To open stability conditions. One is called S1 and says that if we have a subspace in the left vector space such that A of S is 0 and B of S is also 0 and it is invariant with respect to V1, then S must be just trivial. And S2 is sort of dual condition. And in ADHM, you also may recognize this. So if some vector space T lies in C V2 and A of C V1 lies in T and also A of C lies in T and also T is invariant, then T is everything. But
for this
pardon me? Second, please. Yes. Yes.
Capital A, B, lowercase a, b, h, m.
So
Right.
you ask how this arises from ADHM? Or you answer how it arises from ADHM?
I'm trying to verify what is the precise relation to ADHM.
I'll tell you afterwards. Yeah. If you, maybe I should say that the relation to ADHM is of historical nature. Okay. And
also very particular ADHM. Very particular ADHM. Because as you see.
Yeah. So the theorem by Nakajima and Takayama is that, well, this is true. That what I wrote here is the same as what I wrote there. Maybe let's say triangle is isomorphic. No. And well, let me write down formula for this. But maybe before I prove this, let me explain why one should care. For example, now the moment map from A, B1 to A, B to well, equals just B1 and B2. B1 times B1, B2. Okay. Now if V1 equals V2, then from that point of view, given U in GL D1 and X in GL D1 and I in C D1 and J in C D1 dual, I set A B1 B2 A B is equal to U. So in particular, you see that A must be invertible, right? And this only follows from those stability conditions. Certainly not from this quasi-IDHM equation where it would take everything zero. Only the stability conditions guarantee that A is invertible. So it's U, then the conjugate of X, then X minus IJ, then I, and then GU. Okay. And if V1 is bigger than V2, then the formula is somewhat similar but more involved. Pardon me?
And say, can we replace the stability condition with the requirement that A is invertible, or it is not equivalent?
In this, no, I'm not sure it's enough. But anyway, in the next case, when V1 is not V2, then A certainly cannot be invertible. It's only maximal rank. And still you need some more requirement.
Значит, в чем смысл того, что ты сказал, что если бы 1 равно V2,
Ага.
ты просто предъявил вот эти самые все
Да, просто это явно
матрицы, которые удовлетворяют этому уравнению условиям стабильности, да?
Да, да. И они все имеют такой явный изоморфизм справа налево. So, if V1 is less than V2, then this slotted slice over there, what was it? V2 minus V1.
Sorry, Mish, once again.
Yes.
And so you say that B2 is X minus AJ, yeah? IJ.
B2, yes.
Yes. And why not X?
Well, if you plug this into an equation, you will get, this equation will be satisfied by those guys. And,
Because of plus AB term.
Yeah.
Which will eliminate it.
Okay, so this slice, this is the set of V2 by V2 matrices on form X equals, so you'll have certain block structure. This will have V1, this V2 minus V1 rows, this again V1, this V2 minus V1 columns, and here you will have something H. Here you will have only the last column, G1 and so on, G, V1 and zeros everywhere else. Here only the first row, F1 and so on, V1 and zeros everywhere else. And here you will have sort of constant slice. So you'll have the constant scalar diagonal, then ones below diagonal, zeros, and then the scalar next diagonal, and so on. And here E, V2, minus V1. Okay, so having said this, U in GL V2 and X in S, this slice, will go to A equals negative U inverse 1 zeros. B1 will be negative H, this H. B2 will be negative U inverse X U. A will be 0, B1, then just 1 unit, and then all zeros. And finally, B will be negative F1, and so on, FB1. Okay?
Why do you have all the minuses in front of these? You could have changed the sign, right?
Yeah, I could have changed the sign here, here, and here, for example.
Yes,
Yeah?
yes.
Yes, I could.
All the three.
Yes, I could, yes. But it's better this way. What shall I add? Maybe I should add here that if V1 is bigger than V2, then put A equals identity V2 and then all zeros. And B1 equals U inverse X U, and B2 equals H. So it's just like suggested, no minus signs anymore. And A equals G1 and so on, G V2, and B equals 0 V2, and then zeros and only unit at the end. Well, for S as above, with V1 and V2 swapped. Okay. There we are. And this might be useful because it is written down nowhere at the moment, except for the secret Nakajima text about orthosymplectic varieties.
Just so this you say that what is this matrix X? It
Yes.
corresponds to an element of this S, yeah?
Yes. Mm-hmm.
And you said that S is symplectic.
No, not S itself, but the product of the slice and the group. The equivariant slice is symplectic.
Product of
S itself is a highly non-symplectic. It has a big Poisson center. Only the product. Yeah, for example, S can have odd dimension. Like if you take
that I wanted to say. So and so the dimension of S is what is
is the co-dimension of the corresponding nilpotent orbit.
If you want my everything is what the S is up. Then S is just the whole
If V1 is V2 or what?
Let's say if you want it's V2 minus 1.
If V1 is V2 minus 1, yes, then it's the whole. Yeah. Okay, so now what can I say? We already defined the both varieties there, and then we can mention the original theory by Cherkis, that the co-balanced both varieties meaning that whenever we have a triangle part, then the two V1 equals V2. Okay. So this class is nothing but the covariates. Namely, if we have any fragment like this, V, well, okay, V anything, and then frame capital N, and then it goes to the left and to the right. So this particular part goes to V, V, so on, V, just N, many triangles. And this is, if you think of it maybe in the morning, then it's absolutely evident. Because what is this thing? This thing is just the cotangent bundle of GL n times cotangent bundle of Cn, or maybe V, I should say. V. And then by definition, you reduce by GLV. So if you reduce by GLV, you kill this part, and you just acquire more and more and more these parts, and altogether you acquire the cotangent bundle to CV tensor Cn, and that's what you yes, that's what you have in the definition of Euler variety. So it's a little.
Could it be seen from this picture?
No, at least I cannot see it from that picture. I can only see it from this picture, and not at this time of the day, but in the morning. And then there is a dual theorem of Nakajima, Takayama. Says that balanced both varieties again meaning that any two-way part has the same V. So V1 equals V2 for any two-way part, bi-fundamental part. Is the Coulomb range of the corresponding Euler gauge theory. And again, just whenever you have this fragment of the quiver, it goes to just
this theory is also
so Yes, there is a theorem, Юлия Качева Такая. Yes, and in other words, symplectic duality on both varieties just swaps this and that. Whatever you have here, V1, V2.
Если не понял, как у тебя в терминах этих толчалных многообразий, у тебя две одинаковые картинки.
No, here you have non-triangle parts. Here you have
this is a term of both varieties, yeah? And
yes.
What
So you start from some quiver. Given a quiver, you can consider either Higgs branch of this quiver, that is quiver variety, and this would be such a bow variety, or Coulomb branch. And Coulomb branch would be a bow variety where you swap triangle and two-sided parts.
So, does it mean that if we have like difference D in our, like, for example, Higgs variety, then the Coulomb dual will be not a quiver, because we can't construct
Not a what?
not a quiver, because in terms of
Yes. Some Coulomb branches certainly they are not quiver variety. Yeah. For example, you can consider you can start with a quiver without framing. No frame at all.
Я что-то в это время дня совсем уже ничего не соображаю. Значит, я такое предыдущее объяснение так, что вот этот колчан означает, что у тебя есть теория с калибровочной группой СУВ, да, и N мультиплетный.
Да.
Ну, по крайней мере,
Да,
ладно,
да.
кусочек теории. И ты говоришь, что ты по ней можешь построить кулоновскую хиггскую ветку. Уж как мы не знаем, но как ты можешь.
Да, и можно их прямо явно вычислить как луковые многообразия.
Да, и это вот в этом подтверждение этих теорем
Да.
главных Накаяма, Такаджина и так
Да.
далее. А теперь, что такое кулоновская колчана, я не понимаю.
Нет, почему без колчана? Не бывает без колчана. Начинаешь с
А
колчана.
ты только что сказал, что бывает, или я не понял.
Ты начинаешь с колчана и по нему рисуешь лук. По колчану рисуешь лук. И этот лук дает кулоновскую ветвь этого колчана. Например, если нет no framing, means that you will obtain the corresponding Coulomb branch just without by fundamental parts. So you'll have only non parts: V1, V2, V3. V4, V5, like this. And if you draw it that way, you'll have, well, let's see, V1 goes to C, V2, that's A1, B1, B2. But you also need those triangles. And then we'll go by A2 to C, B3. And again, you will have those triangles and so on. Well, and then you close it up. Circle. And, well, this picture can be directly related to ADHM presentation, only with triangles. And this was historically how it first appeared in the works of Leonid Rybnikov.
But what will happen if we have like V of, for example, like triangle V, but it is like closed path? I mean, if in all these cases V1 equals V2 equals V3, is it also
it's only some very particular Zastava space. But it's not a Quiver variety. Okay, so we're almost done. Now, the one funny thing is that there are unexpected isomorphisms between both varieties. Namely, so-called Hanani-Witten transitions. So they're of local nature, and they say that whenever you have a part like this, V1, bifundamental V2, triangle V3, then such a Bow variety is isomorphic to V1, triangle part V2 prime, two-way part V3, where V2 prime is V1 plus V3 minus V2 plus 1.
Это вот там мне какую-то брану куда-то передали?
Да. But it is theory by Nakajima Takayama.
But it should be like a relation.
In the Moore Chikawa category,
Yeah.
Yeah, there is such a unexpected relation in Moore Chikawa category. Let me close up.
And if we compare it because V2, it's some kind of self-duality.
Yes. So, an example. This example demonstrates the power of Cherkas's, Nakajima, and Takayama theory. So let's consider the usual Higgs branch of this quiver gauge theory. And there is framing in the middle. Okay? So this is the usual quiver variety. Yeah? Higgs branch, quiver variety. So what do we know? So by Cherkis, by this Cherkis, it is isomorphic to what should I say? Maybe 0, 1, 2, then 2, then 2. So well, this is the recipe, Cherkis recipe. That's I'm applying. Then 1, and then 0.
Можно, может здесь не так быстро. Значит, у тебя там была двоечка, и ты, значит, по этой самой не должен эту двоечку 2 раза должен нарисовать.
No. The number n is number of triangle parts. There are 2 triangle parts. Framing is 2, so it's two triangle parts.
2 triangle parts. And how this кружочки?
Yeah, so these are just 2-way parts. Well, this go to 0 if you want. Go to 0 if you want.
И что ты сделал? Но это же какие-то манипуляции с кулоновской веткой были, нет?
No. That's just Cherkis. This is absolutely very elementary. It's Higgs branch, nothing to do with Coulomb.
Yeah, but I thought that by this procedure you can add only this with crystals.
Right. So that's what I did. I started with this non-framed part, For non-framed part, I just have by fundamentals, just by definition. Variety. But then framing.
Чертиса добавить.
Yeah.
Там, по-моему, в теории Чертиса формулировка ничего про эти произведения с кружочком, как они two-way, да?
Yes, yes.
Ничего не было сказано.
Что ты делаешь?
Sorry, maybe I should have added this. So, whenever you have such a part, then you just write.
Да, теперь понятно, да.
Yeah, so the same applies to the dual, the Kajima-Takayama theory. Okay, so then by Hanani-Witten, you can move all the triangle parts to the left. Using this Hanani-Witten transition, you can move over there. What you will get is a how should I say this? Not transition, but move. Yeah. Well, the official name is transition, but you can also call it move. So you go to 4, then from 4 you go to 3, 2, 1, 0. Very good. Now, you split into 2 parts, like this. So you have something like x times y, and then introduction by G of 4. Now, y is another quiver variety, but this quiver variety, when I have n and -1 and -2 and so on to 0, this is just an important code. So this part y is just an important cone of GL4. This, well, if you wish, this craft purchase. Okay, and that part, x, just, well, maybe it's sort of lemma. Whenever I have 0, V1, V2, V3, and then you can continue or you can stop here, for example. So it will be always isomorphic to GL V3 times a certain slice as lambda. So lambda is the partition V3 minus V2, V2 minus V1, then V1, but only if it's a partition. So if V3 minus V2 is bigger than V2 minus V1, bigger than V1. So it's more general. We started with the elementary num or triangle part, which was an equivariant slice, but only for the hook partition. But if you compose a few triangle parts in this favorable case, then you will get more general equivariant slice. Okay, so in particular, in this particular case, it means that x is just GL4 times the slice 2, 2. Okay, and so I have to take the product of this and that, and the reduction by GL4. Well, the reduction by GL4, it imposes certain moment map equation and quotients out by GL4. So when you quotient out by GL4, you will just kill this GL4, But the moment map equation is just the equality. The left moment map is equal to the right moment map. So in the right moment map you have some input matrix. In the left you have this slice. So in other words, what you get is the product, not the product, but just intersection S22 with an input called GL4. And that's the answer. That's the heated branch in question. So that's just the Euler variety, but when you define it with in other words, it can be written as S22 intersect with all 4. So it's what we started with, intersections of totally slides and orbits, but this is an effective computational way to
Completion. Some completion of the intersection with the numbers. What do you know by the bar over O?
The closure, so it's the whole important code. Is that the maximal orbit and its closure, the whole important code. And that's it. Thank you very much.
The result is a complex.
Pardon me?
The result is a complex.
No, why? It's not complex, it's a fine. It's a fine, but not complex at all. The same with Uhlenbeck. The so-called Uhlenbeck computation is in fact in a fine variety, not compared at all. It's an affinization of a instanton moduli space, which is not a fine.
When in the beginning you said that such intersection can be identified with some variety, you meant the way back or something different?
I mean, how given an intersection, how to find the corresponding, I can...
There's something different, yeah?
No, well, it's the result is equivalent, so to say. And I can, if you want, I can tell you which.
And the result, as I understand, that what you said, that for this intersection to give, yeah, just to present the corresponding variety, you don't need this Hanani-Witten and...
No, it's just, I just use it as to demonstrate the usefulness of Hanani-Witten presence for effective calculations.
And what is the way from this picture to go back?
To go back, okay. Let's go back.
So, is it clear when, in terms of this broad variety, the variety itself is what simple way?
Is what?
In what simple way? For example, when we consider this two left and right party, is it clear why the left party is easy to calculate? The right ways.
No, maybe I don't know. I don't know. The logic is that, at least for some similar question, the logic is that it is hard to calculate the Coulomb branch, and the both varieties are relatively simple. At least they're given by some standard invariant theory algebraic geometric procedure. And the Coulomb branch is something like a black box. But sometimes it helps in the opposite direction, surprisingly. Well, we start from mu and lambda. Mu is bigger than lambda. Two partitions of M. And then we assign to them certain dominant weights over, let's say, GL n. Right? Like mu1 minus mu2 omega 1 plus mu2 minus mu3 omega 3 plus so right? And so the same with lambda. So, well, it's mu, but viewed as a weight of GL. And the same we do with lambda. Then we can use that mu is bigger than lambda. So mu minus lambda is certain alpha, which is a positive combination, linear combination of simple roots of GL. So it's the sum of mi omega I, it's the sum of li omega I, and this is the sum of ai alpha I. And then we draw the corresponding quiver. So it will have A1, and then M1, A2, M2, and so on. Okay, and the Coulomb range of this theory will be equal to the intersection of O mu bar with S lambda. Okay, and hence the Higgs branch of this theory will be equal to the intersection of O lambda transposed with S mu. So if you wanted to realize the intersection of some orbit with a slice as a Higgs branch, so that this is the recipe.
И там у нас лямбда транспонер, значит, кто там, мю это 2,2, да? В том примере.
But 2 is self-conjugate.
Yes. Да. Поэтому, лямбда у нас там. Давай проделаем эту упражнение. Чтобы надо мне оставить.
So, it looks like this mu will be 2, and lambda will be 0, right? As lambda, but unfortunately it's not, sorry. So I want my lambda transposed to be 4, and mu transposed to be 2, right?
Mu 2,2 мы вроде выяснили, да?
Yes, and hence mu will be 2, and lambda will be 1. Okay, and what does it mean? I have to subtract. So when I subtract, what do I get? 2, 2 minus 1, 1, 1.
No.
Uh, mm,
What do you need to subtract?
just by this.
Я даже
Recipe.
сами формул не понимаю. Кто это будет взять? Ми1 минус 2 на омега-1. Ноль.
It's
One,
1,
one, one,
negative
one,
1, negative 1, right? And so it's mu minus lambda.
Мгм.
And what is this? It's like well, epsilon 2 minus epsilon 3 plus epsilon 1 minus epsilon 4. And this is alpha 1 plus alpha 2 plus alpha 3, and this is just alpha 2.
Ну да.
So you will get alpha 1 plus 2, alpha 2 plus alpha 3. And you see miraculously,
Мгм.
it's just what we, 1 to 1, just what I have. So even at this time of the day, yes. So I think at this triumphant moment we should stop. Thank you.
Спасибо.